Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to start by visualizing something for a second. Just picture the Milky Way on a perfectly clear, dark night.
Right, like you have to be far away from any city lights for this to really work.
Oh, absolutely. You need that pitch black sky. And you look up and you see that incredible glowing band stretching right across the sky.
It's stunning.
It is. And if you've ever really looked at it, like really stared at it, you've probably noticed that it looks kind of cloudy.
Yeah, I mean, it literally looks milky, which is obviously how it got the name in the first place.
Right. And for a long time, it was super easy for humans, even, early astronomers, to just assume that cloudiness was, well, just a trick of the light.
Or maybe just the way billions of distant, faint stars sort of blur together in our primitive optical vision.
Exactly. Like back in the late 1700s, the astronomer William Herschel famously looked at these dark patches in the Milky Way through his telescope, and he declared them holes in the heavens.
Which is such a poetic way to put it, honestly.
It really is, but he literally believes he was looking through a gap in the stars, like right out into empty space.
Right, he thought the dark spots were just voids.
Yeah. But that milky texture and those dark voids, they aren't an optical illusion, and they definitely aren't a gap.
No, not at all.
They are actually these vast, sprawling clouds of cosmic dust. And here's the thing that just completely rewires how you have to think about the universe.
Okay, let's hear it.
That dust is hiding a massive, almost incomprehensible secret. It is literally acting as a curtain that obscures roughly half of all the light coming from galaxies in our universe.
Which is just, it's a staggering amount of missing data, if you think about it.
Right. Half of the universe's light just hidden behind a veil of cosmic soot. So we are going to explore how a monumental new project, like a literal 50-meter colossus of an instrument called the Atacama Large Aperture Submillimeter Telescope.
Or AtLAST, for short.
Yes, AtLAST. We're going to see how it plans to finally pierce through that dusty curtain and, map the missing half of the universe.
It really is a profound realization when you grasp the sheer scale of what we haven't been able to see. I mean, you're talking about half of the cosmic information being essentially redacted by dust.
Redacted is a great word for it, like it's classified information.
Exactly. And if we don't find a way to see that hidden half, our current understanding of the cosmos, of how galaxies form, how stars are born, it's fundamentally biased. It's incomplete.
So we're just working with a fraction of the fact.
We are trying to understand the entire evolutionary history of the universe while only being able to read every other chapter of the book.
Okay, let's unpack this, because logically that makes me question pretty much every textbook image I've ever seen.
As you should.
So when I look at those iconic high-resolution space images like the Hubble Deep Field or, those sweeping optical panoramas of spiral galaxies, am I literally missing half the picture because of space dust?
You are.
Are we just flying completely blind in those heavily obscured regions? Or do we at least have some mathematical models to, guess what's behind the curtain?
Well, we have models, sure. But models based purely on optical light are heavily skewed. So yes, in many ways, we have been flying completely blind in the optical spectrum.
Wow.
And the problem is really how we traditionally think about space dust. We tend to conceptualize it like, dust on a camera lens.
Right, like a smudge that you just wish you could wipe away so you could see the real stuff behind it.
Exactly. But what's fascinating here is that the dust isn't just an obstacle in the way. The dust is the very material that shapes galaxies.
It's the building blocks.
It is the active ingredient. When we talk about this dust towards the center of our galaxy, and indeed most galaxies out there, we're talking about the fundamental building blocks of the universe.
Okay, so it's not just getting in the way, it's doing the work.
Exactly. Claudia Saccone, an astrophysicist at the University of Oslo, has made this point incredibly forcefully. She notes that without a submillimeter telescope capable of seeing through this, we're getting a very, very biased picture of what's out there.
Because we're only looking at the clean, dust-free spots.
Right. We are entirely missing the regions of space that are the most obscured by dust, which, coincidentally, are the exact regions where the most crucial cosmic action actually happens.
I want to make sure I'm picturing this dust correctly, though, because when I think of dust on Earth, I think of, dead skin cells and dirt under the couch.
Right, yeah. Completely different things.
What exactly is cosmic dust? Because if it's blocking half the light in the entire universe, it must be unimaginably dense, right? Like a cosmic brick wall.
It's not dense in the way we think of a brick wall, no, but it is incredibly pervasive. Cosmic dust is, well, it's entirely different from household dust.
Okay. So what is it made of?
It's primarily composed of microscopic grains of carbon-like ultrafine soot and silicates, which are essentially microscopic sand grains.
Sand and soot.
Yeah, and they're often coated in a mantle of water ice or frozen carbon monoxide, and they are tiny.
How tiny are we talking?
We're talking about particles a fraction of a micron across.
Yeah.
That's smaller than the particles in cigarette smoke.
Whoa. Okay, so it's really more like smoke than dust.
Exactly. The reason it blocks so much light isn't because it's packed tightly together like concrete. It's because there are trillions upon trillions of miles of this smoke.
Oh, I see. It's the depth of it.
Yes, and it's not a uniform fog either. It clumps together in these vast molecular clouds.
So it's less like a brick wall and more like, say, a colossal interstellar smoke cloud from a wildfire.
That's a great way to picture it.
Like, you might be able to see a bright flashlight a few feet away through the smoke, but a streetlight a mile away is completely gone.
Exactly. And to follow your smoke analogy, think about what is actually causing that smoke.
The fire.
Right. In space, these dense, dusty clouds are the active stellar foundries. They are the fires. You're seeing the brightly burning, mature stars outside the clouds.
The finished products, basically.
Exactly, the finished products.
Yeah.
But you're totally missing the cold gas and the dust inside where new stars are actively being forged.
Because the light just can't get out.
Right. The visible light from those stellar nurseries is buried. The dust literally absorbs the high-energy ultraviolet and visible light emitted by those young, hot stars.
Okay, wait, hang on. If the dust absorbs the light, energy is conserved, right? That's basic physics.
Yes, absolutely.
So where does that energy go? The dust has to do something with all that absorbed starlight.
And that is the crucial piece of physics here.
Yeah.
The dust grains absorb that visible light, and it heats them up.
Okay.
But they don't get hot enough to glow visibly like a star. Instead, they re-emit that energy at much longer wavelengths.
So it's invisible to us.
Yes, to human eyes.
Yeah.
Specifically, it re-emits in the far infrared and submillimeter range of the electromagnetic spectrum.
Submillimeter.
Right. So to a traditional optical telescope like Hubble, that dusty area just looks like a dark, empty void.
It looks like Herschel's hole in the heavens.
Exactly. But if you put on quote-unquote submillimeter goggles, that same dark void is glowing fiercely with thermal radiation.
So it's not empty at all.
It is the most densely packed, active environment in a galaxy. If we ignore the dust because we can't see through it optically, we're ignoring the factories of the universe.
That feels like a massive historical vulnerability in our science.
It really is.
I mean, if half of the data has been missing this whole time, if we've only been able to measure the light that didn't get absorbed by dust, what does that mean for our current mathematical models of the universe?
It means we have to take them with a grain of salt.
Because we've built these incredibly complex theories about how galaxies evolve over billions of years, but you're telling me the math is based on a fundamentally biased sample.
It means that our models are heavily skewed toward the processes that happen to emit light we can easily see. It is the literal textbook definition of observer bias.
Right. We only measure what's easy to measure.
Exactly. Imagine trying to understand the economy of a major city, right? But you are only allowed to look at retail stores.
Okay.
You're completely ignoring the factories, the shipping ports, the agricultural sectors, all because they are behind locked doors.
You'd think the economy was entirely driven by people buying, sweaters and coffee.
Exactly. You'd have a totally warped view. We built our understanding of cosmic evolution based on the light that makes it to our optical telescopes. But what if the most important phases of a galaxy's life cycle happen when it is completely shrouded in dust?
Which you just said they do, the star foundries.
Right. What if the mechanisms that determine why a massive galaxy suddenly stops forming stars, or why it grows to a certain size, are all hidden in that missing half of the light?
Then our whole timeline is just wrong, or at least patchy.
Without this complete picture, our cosmic timeline is full of massive unverified gaps.
So if the dust is the problem, and we've mathematically known it's a problem for decades, why is this suddenly a solvable problem now?
Well, technology catches up.
But we have incredible technology already. We have telescopes scattered across the planet and floating in space. Why couldn't we just build a bigger, better optical lens to, I don't know, brute force our way through the dust?
Because brute forcing it with a bigger optical lens violates the laws of physics.
Okay, that's a good reason.
Yeah, you can't see through a wall just by staring at it harder.
Fair point.
The physical size of the dust grains happens to perfectly scatter and absorb the wavelengths of visible light. It's known as Rayleigh scattering and Mie scattering.
So visible light is just the wrong tool for the job.
Exactly. To see through that specific type of cosmic dust, you have to look at a completely different type of light. You need a wavelength that is physically longer than the dust grains themselves.
So the wave just kind of steps over the dust?
Essentially, yes. The wave washes right over the grain without being absorbed. You need to look at radiation that falls exactly between radio waves and infrared light on the electromagnetic spectrum.
And these are the submillimeter waves?
We call these submillimeter waves, yes.
Okay, so we need a completely different type of receiver. But I know we already have telescopes that do this.
We do.
Astronomers currently use a massive facility in Chile called LMA. That's the Atacama Large Millimeter Submillimeter Array.
Right.
And from what I understand, it is an absolute powerhouse. It's this huge network of 66 separate antennas all working together as an interferometer.
It is an incredible machine.
So if we have LMA, why on earth do we need AtLAST?
Well, Tony Mrozkowski, an astronomer at the Institute of Space Sciences in Spain, pointed out a really critical flaw with LMA if your goal is large-scale mapping.
What's the flaw?
He essentially said that LMA is a microscope.
A microscope, okay.
Yeah, it can only see an area that is thousands of times smaller than the surface of the moon in the sky during any given observation.
Wow, thousands of times smaller than the moon.
Yes. And to understand why LMA is a microscope, you have to look at how an interferometer actually works. LMA isn't one giant dish, right? It's 66 smaller dishes.
Which are mostly 12 meters across, I think.
Right, 12 meters across, and they are spread out over distances up to 16 kilometers.
Okay.
By mathematically combining the signals from all these separate dishes, astronomers create a virtual telescope that has the resolution of a single telescope 16 kilometers wide.
Which is how they get those insanely sharp images.
Exactly. It provides unprecedented, wildly sharp resolution.
So it can zoom in incredibly far. It can basically pick out a grain of sand from miles away, so to speak.
Precisely. If you know exactly where a specific young star is forming, and you want to zoom all the way in to see the specific delicate disk of dust swirling around that single star.
To see, like, where a planet is forming.
Exactly. If you want to see that, ALMA is your tool. There is nothing better on Earth. But the trade-off in physics is that the field of view, the actual patch of sky a telescope can see at one time, is dictated by the size of the individual dishes.
Oh, because ALMA uses 12-meter dishes.
Its field of view is incredibly narrow, so if you don't know where to look in the first place, ALMA is not going to help you find it efficiently.
It sounds like trying to map the entire topography of the Earth by looking through a microscope lens.
That's a really good analogy.
Like, sure, if you drop the microscope on the ground, you're going to get an absolutely breathtakingly detailed view of a single leaf.
Oh.
Or, you know, the microscopic veins of a single blade of grass.
Right.
But it would take you a million years of dragging that microscope inch by inch across the dirt to figure out you're standing in a massive forest, let alone to actually map a continent.
That is exactly the problem. LMA is the microscope. But what astronomy desperately needs right now to fix our biased timeline of the universe is the wide-angle camera.
And that is AtLAST.
That is what AtLAST is fundamentally designed to be. It's not trying to replace LMA at all.
They do different things.
Right. It's trying to do the job LMA mechanically cannot do because of the laws of optics. AtLAST wants to take a true census of the entire universe. Mrozkowski even joked that with AtLAST, they will be able to map the hell out of the universe.
I love that. Map the hell out of it.
Yeah, and to give you a sense of the scale difference, while LMA sees a fraction of the moon, AtLAST will be able to image an area up to 16 full moons in size with every single observation.
16 moons in a single frame. That is a massive leap.
It changes everything.
Let's really paint a picture of what that difference in scale means for how science is actually conducted, because I think people imagine astronomy is just looking wherever you want.
Right, but telescope time is precious, and you can only look at so much.
Exactly. So imagine you are an astronomer scanning the night sky. With LMA, it's like looking at the sky through a tiny pinhole poked in a piece of cardboard.
Very tedious.
Yeah, you point it, record data for hours, move the cardboard a fraction of an inch, look again, move it again, look again for years, just to map a tiny patch of blackness.
Right.
But with AtLAST, you are suddenly throwing open a giant panoramic bay window.
And throwing open that bay window changes the very nature of the scientific method you apply.
How so?
Because when you're looking through a pinhole, you only point your telescope at things you already know are interesting.
Because you can't afford to waste time looking at nothing.
Exactly. You look at targets you've theoretically predicted based on previous optical surveys. You say, let's look at this specific coordinate because Hubble saw something weird there.
But wait, wouldn't that just reinforce the bias we were talking about earlier?
It absolutely reinforces the bias because you're only looking where optical light already told you to look.
Oh, wow. Yeah.
But with a massive field of view, 16 moons across, you don't need a target. You do what's called an untargeted survey.
You just cast a wide net.
You just sweep across vast, seemingly empty stretches of the sky and see what's actually glowing in the submillimeter. You capture the context. You see how different dusty galaxies cluster together over massive cosmic distances.
You discover entirely new classes of objects that you didn't even know you should be looking for because you finally have the peripheral vision to spot them.
Exactly. You map the cosmic web. But opening that bay window requires an engineering marvel of just staggering proportions.
And this is where my mind really starts to break, honestly, because the physics of building this thing sound contradictory.
They are definitely challenging.
To get that massive field of view without using an interferometer like ALMA, you have to build a single gargantuan dish. AtLAST is designed as a 50-meter single-dish telescope.
Yes.
50 meters. That is more than half the length of an American football field.
It's massive.
And the mirror itself features these precisely machined aluminum panels, all supported by a massive, incredibly rigid steel backing structure.
Right.
The entire apparatus is projected to weigh an incredible 4,400 tons. And to make that wide-angle view possible is not just the primary dish, right? It includes a 12-meter secondary mirror suspended in the air above the main dish.
Correct.
A 12-meter mirror all by itself is larger than the primary mirrors of most of the world's most famous telescopes.
Yes, the scale is industrial, but the precision required is microscopic.
Okay, let's unpack this.
Yeah.
Because logically, moving a 4,400-ton dish with sub-millimeter precision sounds like a recipe for bending the metal.
It absolutely is.
I mean, how does a building-sized steel structure weighing nearly 9 million pounds dart back and forth across the sky to map these 16 moon swaths without literally tearing itself apart from the sheer mechanical stress?
It's a huge problem.
Gravity alone should warp a 50-meter steel dish just by tilting it. Why don't they just build a massive concrete dome, fix it in place pointing straight up, and only move a smaller mirror inside it to direct the light?
You've just hit on exactly why this is arguably one of the most complex mechanical challenges we've ever faced in astronomy.
So why not just lock it in place?
Because you can't just fix the dish pointing straight up. The Earth rotates, and a fixed telescope, which we call a transit telescope, only sees a narrow strip of the sky that happens to pass directly overhead.
Oh, right. You're completely at the mercy of the Earth's rotation.
Exactly. To map the universe efficiently, to do those massive untargeted surveys we talked about, you have to be able to point anywhere in the sky, and you have to be able to sweep back and forth to track objects.
So you have no choice. You have to put this 9 million pound behemoth on a pivot.
Yes. You are taking a colossal mass and subjecting it to constant acceleration and deceleration. The torque on the gears, the stress on the bearings, it is monumental.
I can't even imagine.
And your intuition about the metal bending is completely correct. When you take a 50-meter wide steel and aluminum structure and tilt it from pointing straight up at the zenith to pointing closer to the horizon, gravity pulls on it differently.
The metal just sags.
The metal physically slumps. It warps.
Wait, if the metal is constantly bending under its own weight as it tracks across the sky, how do the sensors even know what perfectly flat or perfectly parabolic is supposed to be in real time?
It's a constant battle.
Because if the surface of the mirror deforms by even a millimeter, doesn't that completely scatter the submillimeter waves you're trying to focus?
It absolutely destroys the image. The surface accuracy of the primary dish has to be maintained to a fraction of the wavelength it's observing.
So how exact does it need to be?
We are talking about maintaining a perfect curve down to tens of micrometers that is thinner than a human hair across a 50-meter surface.
That's insane.
It is. And to solve the slumping problem, you can't just build it thicker and heavier.
Right, because then it's too heavy to move.
Exactly. Eventually, the sheer weight defeats the structural integrity of any steel you use. So instead, you use what is called an active surface.
Okay, what is an active surface?
The 50-meter dish isn't one solid piece of metal. It's composed of hundreds of individual, perfectly machined aluminum panels.
Okay, like tiles.
Like tiles, yes. And beneath every single panel are computer-controlled actuators. Essentially, precision motorized pistons.
Oh, I see where this is going.
Yeah. As the massive telescope tilts and the steel backing structure inevitably bends under gravity or, is pushed by high-altitude winds, a laser metrology system or holography system constantly measures the exact position of every single panel.
Constantly measuring.
Constantly. And the computers calculate the distortion, and the actuators push or pull the individual panels in real time to maintain the perfect overarching parabolic shape.
That is just... It's a living machine.
It really is.
It's like a heavily loaded freight train performing the choreography of a ballet dancer, constantly adjusting its own skeletal structure to fight against the laws of gravity so it doesn't step out of line by the width of a human hair.
It's exactly that. And this is why the project is currently in what is called the AtLAST 2 design phase, which runs until 2028.
So they're figuring all this out right now.
Yes. They aren't just sketching this on a chalkboard. They are actively prototyping the optics, the direct drive control systems, and the structural integrity required to make rapid, massive movements feasible.
But even if you build this perfectly rigid, perfectly acting mirror that can seamlessly scan the sky, it's entirely useless if you put it in the wrong place.
Location is everything.
Right. And a machine this sensitive, this delicate despite its mass, cannot just be built in anyone's backyard. It requires one of the most extreme, inhospitable environments on planet Earth just to function.
Location is the ultimate bottleneck in submillimeter astronomy. You can have the best telescope in human history, but if the atmosphere above it is opaque, you see nothing.
So where does it have to go?
AtLAST is planned to be located near Submillimeter in Chile's Atacama Desert, specifically on the Chajnantor Plateau.
Which is high.
Very high. The site is over 5,100 meters above sea level. That is nearly 16,700 feet.
Oh, wow.
At that altitude, the atmospheric pressure is barely half of what it is at sea level. But more importantly than the thin air, the environment is unimaginably dry.
Let's really drill down into the physics of that dryness, because I want to understand the why.
Okay.
I understand wanting to be above the clouds so it doesn't rain on your 9-million-pound robot. But why does the absolute microscopic humidity level of the air make or break this entire multi-billion-dollar project?
It comes down to quantum mechanics and molecular chemistry. Water vapor in Earth's atmosphere is the arch nemesis of submillimeter waves.
The arch nemesis?
Literally, it's not just a fog, it's a physical barrier. A water molecule, H2O, has a specific shape that gives it a dipole moment, meaning one end is slightly positive and the other is slightly negative.
Like a tiny magnet.
Exactly like a tiny magnet. And because of this structure, water molecules can rotate and vibrate in very specific quantized ways.
Okay, so they spin. How does that block a telescope?
Because to make a water molecule transition from a slower spin to a faster spin, it requires a very specific, exact packet of energy.
Okay.
And it just so happens that the energy carried by a photon of submillimeter light traveling from a distant galaxy perfectly matches the exact energy required to kick a water molecule into a higher rotational state.
Oh, wow.
Yeah.
So when that submillimeter photon hits the water vapor in our atmosphere, the photon is essentially consumed.
Consumed entirely.
Its energy is entirely transferred to the water molecule, making the molecule spin, and the photon ceases to exist.
Exactly. The data from the cosmos is literally erased by the atmosphere, converted into a microscopic bit of rotational heat.
That's tragic for astronomy.
It is, and it's actually the exact same physical principle that makes a microwave oven work in your kitchen. Yes. The microwaves excite the water molecules in your food, absorbing the energy and turning it into heat. If there is water vapor in the air above the telescope, it acts like a giant sponge, completely absorbing the submillimeter waves before they ever reach the 50-meter dish.
So by placing the telescope at 16,700 feet in one of the driest deserts on the planet, astronomers are physically getting above the vast majority of the Earth's atmospheric water vapor.
They are dodging the sponge.
You are getting a pristine, dry view of the universe, essentially getting as close to the vacuum of space as physically possible without actually launching a 4,400-ton machine into orbit.
Yes, which would be impossible anyway.
Right. But that extreme environment introduces a massive modern dilemma.
The power problem.
The power problem. You are putting a wildly power-hungry, heavy, constantly moving machine in a remote, pristine desert located miles up a mountain where there is no existing electrical grid.
None whatsoever.
Historically, running an astronomical facility like that meant burning a tremendous amount of diesel fuel. You would literally have fleets of tanker trucks driving up the mountain every single day just to keep massive generators running so the telescope could move and the computers could process data.
And doing that in the 2040s generation of observatories feels completely hypocritical.
Exactly. How do you power a 4,400-ton behemoth to study the grand cosmic evolution of the universe while actively contributing to the destruction of the very climate you live in?
You can't. And that is why the researchers working on the AtLAST T2 design phase are making a profound shift in how big science operates. The project is aiming to operate without any fossil fuels whatsoever.
None.
None. They want to use 100% renewable energies.
Which, sounds great on a press release, but logistically how? I assume massive solar power arrays because it's a high-altitude desert with blinding sun?
That's step one, yes.
But solar only works during the day and astronomy happens 247? Especially submillimeter astronomy, which isn't affected by daylight the same way optical astronomy is, right?
Exactly. They observe day and night.
So you need massive energy storage. Normally, grid-scale storage means giant banks of lithium-ion batteries.
They will use advanced battery storage to smooth out the immediate loads, yes. But batteries have limitations, especially in the freezing cold nights of the Atacama, and they degrade over time.
So what's the alternative?
The solution they are bringing to the table is far more revolutionary. They are planning to use metal hydride technology for long-term energy storage.
Okay, what exactly is metal hydride? Because it sounds like something from a sci-fi warp drive. How does it store energy differently than a lithium-ion battery?
It's an incredibly elegant application of chemistry. So during the day, you have excess renewable energy from your solar arrays.
Right.
You use that excess electricity to run an electrolyzer, which splits ordinary water into oxygen and hydrogen gas.
Basic chemistry.
Right. You release the oxygen and you keep the hydrogen, which is an incredibly potent fuel.
But storing pressurized hydrogen gas is historically very dangerous and difficult, right? You need massive, heavy, high-pressure steel tanks, and if they leak on a remote mountaintop, it's a disaster.
Exactly. And that is where the metal hydride comes in. Instead of compressing the hydrogen gas into a dangerous high-pressure tank, you pump it into a container filled with specific, specially engineered metal alloys.
What kind of metals?
Often containing magnesium, titanium, or palladium. These metals have a crystalline lattice structure that acts almost like a molecular sponge for hydrogen.
A sponge for gas.
Yes. The hydrogen gas literally permeates the metal, and the hydrogen atoms bond within the crystal structure of the solid metal alloy, forming a metal hydride.
Wait, so you're storing the hydrogen gas as a solid?
Essentially, yes.
Yeah.
It's absorbed into the solid. It's incredibly dense. You can store more hydrogen in a given volume of metal hydride than you can in a tank of liquid hydrogen.
That's amazing.
And because it's bonded within the metal, it operates at very low, safe pressures. It won't catastrophically explode.
But it's safe and dense.
Right. Then, when the sun goes down and you need power to run the telescope through the freezing desert night, you gently heat the metal hydride.
And it releases the gas.
It releases the hydrogen gas back out, which you then run through a fuel cell to generate clean electricity, with the only byproduct being pure water.
So they are essentially building a bespoke, cutting-edge, hydrogen-based, green power plant just to run this eye on the sky.
They are.
But here's where it gets really interesting. The most incredible part of their energy plan, the part that just blew me away from a physics perspective, is their tailored hybrid energy regeneration system.
It's so smart.
Because the telescope is constantly sweeping across the sky, mapping those massive 16-moon fields of view. It has to accelerate and decelerate constantly.
Think about the physics of that mass again. 4,400 tons.
It's massive.
When that mass gets moving, it possesses a staggering amount of kinetic energy. Normally, when you want to stop a moving telescope of that size to reverse direction, you use massive mechanical friction brakes, much like the brakes on a train.
And all that kinetic energy is just lost as useless heat dissipated into the air.
Yes, but with AtLAST, they are treating the telescope exactly like a giant hybrid car.
With the Prius.
Exactly like a Prius.
When you break in an electric or hybrid vehicle, the electric motor runs in reverse. It acts as a generator, turning the car's forward momentum back into electricity to charge the battery.
Right.
They are doing the exact same thing, but with a 4,400-ton space telescope. It breaks, and it powers itself. It uses its own immense weight and inertia to generate the electricity needed for the next sweep across the sky.
It is brilliant engineering, and it forces innovation. By putting a hard constraint on the project saying, we will not burn fossil fuels, they are forced to engineer a more elegant, efficient machine.
It's a win-win.
And if we connect this to the bigger picture, here's where the physics loop perfectly back to the astronomy.
Okay, how?
Capturing that kinetic energy electrically isn't just a green initiative, it is a scientific necessity. If they use traditional friction brakes, stopping 4,400 tons would generate massive amounts of ambient heat right next to the dish.
Oh, and earlier we established that submillimeter telescopes are essentially looking for the faint thermal heat signatures of coal dust.
Yes.
So if your own brakes are glowing hot in the infrared, you're literally blinding your own telescope with thermal noise.
Exactly. The ambient heat from traditional brakes would completely interfere with the pristine observations of the cold universe. The sustainable choice regenerative braking is actually the superior scientific choice. The engineering solves multiple problems at once.
Okay, so let's synthesize where we are. We have this fast-moving, metal hydride-powered regenerative braking, 50-meter active surface eye sitting 16,700 feet up in the driest desert on Earth, safely above the atmospheric water vapor.
That's the machine.
When we finally turn this perfectly cooled submillimeter precise machine on and we point it at a patch of sky that looks completely empty to optical telescopes like Hubble, what does the raw data actually look like? What exactly are we going to see hidden behind the curtain?
The primary driving goal of AtLAST is to definitively smash what astrophysicists call the confusion limit.
The confusion limit. It sounds like a psychological term, but I assume it's a mathematical one.
It is deeply mathematical, rooted in the Rayleigh criterion for angular resolution.
Okay, simplify that for me.
When we use current submillimeter telescopes to look out into the deep early universe, we detect a generalized glow. We know a submillimeter light is arriving from these deep, heavily obscured, deeply dusty regions.
Right, the submillimeter glow.
But because current wide-field telescopes don't have a large enough aperture, large enough dish, the resolution is poor.
So it's blurry.
Exactly. The light from distant sources spreads out into wide overlapping disks of light on our sensors.
Let me try an analogy to make sure I understand the mechanics of this. It's like looking at a distant city through a thick, heavy fog from an airplane.
Okay, I like where this is going.
You look out the window and you can see a general bright glowing haze on the ground. You know a city is there, but because the light is scattered and your vision is limited, you've absolutely no idea if that broad glow is being produced by 1 million individual porch lights spread out over suburbs.
Right.
Or 100 giant stadium spotlights in a dense downtown, or just one absolutely massive raging industrial bonfire. The light is just blended together.
It is a perfect functional analogy. The sources are blended. Claudia Saccone described it exactly this way. Right now, when astronomers look at a blurry submillimeter patch in the sky, they literally cannot tell if the light they are detecting is coming from one massive hyperluminous galaxy, 10 average-sized galaxies, or 1,000 smaller dwarf galaxies all clustered together in the same line of sight.
They are confused.
They are confused. That is the confusion limit.
And AtLAST cuts through that fog because a 50-meter dish provides the raw angular resolution needed to separate those points of light.
Precisely. Because of its massive aperture, it will shatter that confusion limit. It will resolve those wide, blurry, glowing blobs into sharp, distinct, individual galaxies.
So it clears the fog.
And the projections for what it will uncover are staggering. Saccone states that AtLAST has the potential to find up to 50 million currently missing, obscured galaxies in just 1,000 hours of observation.
Let me just pause and do the math on that for a second, because those numbers are hard to process.
They're huge.
50 million galaxies in 1,000 hours. That means they will be discovering 50,000 newly identified galaxies every single hour that the telescope is running.
It's an astronomical census.
50,000 an hour. But I want to push back on this purely from the perspective of scientific value. How does knowing there are more galaxies actually change the game for us?
It changes everything about cosmology.
Does finding 50 million more galaxies just mean we have to update the cosmic census? Or does mapping these specific dusty galaxies fundamentally change our understanding of physics?
It completely revolutionizes our physics, specifically concerning the largest mysteries in cosmology, dark energy and dark matter.
Really? just by counting them.
It is not just about counting the galaxies. It is about mapping their precise three-dimensional distribution over cosmic time.
Okay, break that down for me. How does finding dusty galaxies help us figure out dark energy, which is the mysterious force pushing the universe apart?
Because dark energy acts on the large-scale structure of the universe. When you can see individual dusty galaxies instead of a blurry blob, you can measure their redshift.
Redshift being how much their light has been stretched by the expansion of the universe.
Exactly. Because looking far away in space is looking back in time, seeing 50 million of these galaxies at various distances allows us to map exactly where matter was clustered at different epochs in the universe's history.
Ah, so we are looking for patterns in how they cluster together.
Yes. Specifically, we are looking for baryon acoustic oscillations.
Baryon acoustic oscillations, what are those?
In the very early universe, sound waves rippled through the hot plasma. When the universe cooled, those ripples froze in place, creating a preferred distance at which galaxies tend to form relative to one another.
Like a cosmic yardstick.
That's exactly what astronomers call it,
Wow.
a cosmic yardstick. By measuring how the apparent size of that yardstick changes across those 50 million newly discovered dusty galaxies at different distances.
You can calculate exactly how the expansion rate of the universe has changed over time.
Precisely.
And because dark energy is what is accelerating that expansion, having a vastly more accurate map of the expansion rate allows us to test our theories of what dark energy actually is.
We are literally weighing and measuring the invisible forces that dictate the fate of the cosmos.
That is just, it's mind-blowing.
Exactly. And it doesn't stop at dark energy or the galaxies themselves. AtLAST will also hunt for literal missing matter in the circumgalactic medium.
Missing matter, like dark matter.
Not dark matter, normal matter. For decades, physicists have known there's a massive discrepancy in our models. There is hot and cold gas that should exist around and between galaxies, vast diffuse halos of it holding massive amounts of mass.
But we can't see it.
It has proven incredibly hard to find using optical telescopes because it doesn't shine brightly enough.
But it emits or interacts with submillimeter waves?
Yes. Through a phenomenon called the Sunyaev-Zel'dovich effect, hot gas in galaxy clusters actually scatters the cosmic microwave background radiation.
Oh, interesting.
When we look at that background radiation in submillimeter wavelengths, the hot gas casts a shadow.
A shadow.
Yeah. AtLAST has the extreme sensitivity and the massive field of view to finally illuminate these massive reservoirs of missing gas, balancing the ledger of the universe's mass.
It just feels so vast. We are talking about mapping 50 million galaxies to measure the expansion of space itself.
It is the biggest scale imaginable.
But one of the things that surprised me the most in understanding this instrument is that AtLAST isn't just a time machine looking out at the furthest, oldest reaches of the cosmos.
Not at all.
It's actually a wildly versatile tool. It's also going to be pointing at things happening right in our own cosmic backyard, like our sun, and even looking at the very localized chemical origins of life itself.
Yes, the flexibility of submillimeter waves is remarkable. On one end of the spectrum, AtLAST will study the unseen components of our own sun's atmosphere, specifically the chromosphere.
Why use a submillimeter telescope for the sun? Can't we just look at it?
Because a submillimeter telescope can handle the intense signal of the sun without being optically blinded or physically melted like a visible light telescope would be.
Oh, that makes sense.
So it can observe the variability of solar flares in a way that has never been done before. It can trace the complex, twisting magnetic dynamics that drive space weather.
Which affects us here on Earth.
Right. And then in the same night, they can swing that massive 50-meter dish around, point it deep into the Milky Way, and peer into molecular clouds and debris disks.
Okay, when you say debris disks, my mind immediately goes to a Saturn-like ring of floating rocks. Is that what we're talking about, or is it more like a diffuse cloud of gas?
It is a protoplanetary disk. It is a dense, chaotic, swirling pancake of gas, microscopic dust, and larger pebbles spinning around a very young star.
So it's a solar system under construction.
Exactly. It is the raw material from which planets, asteroids, and comets are actively forming.
And by looking at these regions with submillimeter waves, we aren't just seeing the physical shape of the disk, are we?
No, we are reading its precise chemical fingerprint.
How? I mean, how does submillimeter light tell us about chemistry?
It goes back to the exact same quantum mechanics that makes water vapor in our atmosphere such a problem.
The spinning molecules.
Yes. In the freezing cold vacuum of space, inside these molecular clouds and debris disks, molecules are constantly rotating and tumbling. As they rotate, they emit faint photons at very specific quantifiable submillimeter frequencies. Every molecule, whether it's carbon monoxide, water, methanol, or something more complex, has a unique rotational signature, like a barcode.
Oh, wow. So by tuning AtLAST to these specific frequencies, we can essentially run a spectroscopic analysis on a cloud of dust thousands of light years away and spot the specific molecules that are swirling around a baby star.
Yes. And astrobiologists are particularly excited because AtLAST will have the sensitivity to map complex organic molecules.
So the building blocks.
Exactly. The fundamental prebiotic building blocks of life, like formamide or complex sugars, as they form in the icy mantles of these dust grains before the planets even fully coalesce.
Think about the philosophical weight of that. We're using the exact same massive 4,400-ton mechanical beast to map the dark energy tearing the universe apart.
Right.
And then swinging it around to look into an interstellar chemical reactor to find the exact molecular combinations that eventually make up our own DNA, our own ocean.
It's all connected.
By looking at these debris disks, we are essentially looking into a cosmic mirror. We are watching a time-lapse of our own solar system's ancient past, watching alien versions of Earth being chemically assembled in real time.
It is the ultimate search for our origins. We are tracking the chain of custody of the molecules of life, from the cold interstellar void into the collapsing clouds that form stars, into the spinning disks that form planets, and potentially onto the surfaces of those new worlds.
It's incredible.
Ruskowski specifically emphasized this capability, pointing out that AtLAST will help astronomers answer the fundamental questions of how life actually emerges in the universe and how it develops based on the initial chemical ingredients available in those specific dusky regions.
But, you know, with an instrument this capable, with a field of view 16 moons wide and sensitivity sharp enough to detect complex organics, it feels like the most exciting discoveries probably aren't even the ones they are actively planning for or writing grants for.
Oh, absolutely not.
The entire history of observational astronomy tells us that the greatest science is almost always the stuff we never saw coming.
Without a doubt. When you build a machine that looks at the universe in a fundamentally new way, in this case, conducting wide-field, high-resolution submillimeter mapping at an unprecedented pace, the greatest science will undoubtedly come from the unknown.
The surprises.
Yes. The astronomical community is deeply anticipating unexpected discoveries, particularly transient, short-lived events.
Transients are essentially flashes in the dark, right? Things that happen quickly, release a burst of energy, and then fade away or disappear entirely.
Yes. Imagine a massive star collapsing into a black hole or two incredibly dense neutron stars merging.
Those are huge events.
Massive. They release huge bursts of energy. But if they happen deep behind a thick veil of dust, the visible light of the explosion is completely absorbed. Optical telescopes completely miss them.
But the dust heats up.
Exactly. That absorbed energy violently heats the surrounding dust, causing a massive temporary flare in submillimeter wavelengths.
So it flashes in the submillimeter.
Right. And because AtLAST maps such a huge area of the sky so quickly, it acts like a wide-angle security camera for the universe.
Yeah.
It can catch these transient flashes that only appear at submillimeter wavelengths.
We probably have no idea what's out there.
We have absolutely no idea what mysterious, short-lived, high-energy phenomena are flashing in the dark half of the universe right now, simply because we've never had a wide-angle submillimeter camera to catch them in the act.
And the incredible thing is they are building this to last. They have the time to sit and watch for those flashes.
Decades of time.
Right. This isn't a short-term 5-year space mission where the coolant runs out and the satellite dies. Ruskowski was very clear that AtLAST is designed for a 50-year operational lifespan.
Half a century.
It features a massive instrument cabin that allows for entirely new, completely upgradable detectors to be swapped in as technology improves over the decades. It is explicitly not what he called a throwaway disposable telescope. It's built to evolve.
That's a crucial design choice.
And that leads to a piece of this that I find profoundly inspiring. The human element. This isn't just one country or one university flexing its scientific muscles and hoarding the data. It represents a massive, unprecedented international collaboration.
It really does.
We are talking about institutions in Europe, Japan, Chile, South Africa, Canada, Taiwan, Thailand, New Zealand, the U.S., all bringing their engineering, their physics, and their funding to the table.
This raises an important question, right? What happens when the world actually units to do fundamental science? It is a testament to what global unity can achieve.
Do you have an example of that?
Yeah, a perfect example is the Japanese astronomical community. They had actually been seriously considering and independently designing their own 50-meter submillimeter dish.
Really? A rival project?
Yeah, they called it the Large Submillimeter Telescope, or LST. It was essentially a competing concept. But as Sicone noted, they looked at the immense logistical challenges, the sheer scale of the engineering required for the active surface, the massive costs, and crucially, the perfectly shared scientific goals. And they realized we should join forces.
That is so rare. Usually everyone wants their own name on the building.
Right. The AtLAST T2 design phase isn't just about prototyping structural hardware. It's about doing the diplomatic and organizational work to turn that global cooperation into a concrete shared facility that benefits everyone.
I just want to reflect on the permanence of that for a second. In a world where so much of our technology is entirely disposable, where $1 billion smartphone is functionally obsolete in 2 years, the act of designing and physically building an upgradable 4,400-ton facility meant to serve entirely new generations of astronomers for half a century, that is a profound statement of hope.
It's a commitment to the future.
It's a commitment to the long-term human endeavor of understanding our place in the universe. We're literally designing sustainable energy systems to power a machine for scientists who haven't even been born yet, so they can analyze transient submillimeter flashes that our current physics can't even comprehend.
It guarantees that AtLAST will be a foundational cornerstone of astrophysics for the entirety of the mid-21st century.
It'll be the benchmark.
Exactly. It will work in tandem with the other mega observatories coming online in the 2030s and 2040s, providing the crucial unbiased submillimeter context that massive optical telescopes like Europe's extremely large telescope will desperately need to make sense of what they are seeing.
It's just an incredible sweeping journey of discovery we've mapped out here. We started with the realization that when we look up at the Milky Way, our biological eyes and our optical history have left us completely blind to half of the universe's light because of cosmic dust.
Half of reality just hidden.
We explored how the AtLAST project plans to fix that by moving from the brilliant but narrow microscope view of LMA to a massive 16-moon wide-angle lens.
Opening the bay window.
Yes, exactly. We unpacked the staggering, almost contradictory engineering of moving 4,400 tons of steel and actively warping aluminum panels with submillimeter precision, 16,700 feet up in the Atacama desert to escape the quantum absorption of water vapor.
Beating the sponge.
We saw how it's pioneering sustainable big science with metal hydride storage and kinetic energy regeneration. And we looked forward to the promise of discovering 50 million hidden galaxies to map dark energy, balancing the cosmic scales with missing matter, and tracing the very chemical origins of life in the freezing disks around baby stars.
It's a lot to take in. And as we look toward that future of discovery, I'm going to leave you with a final thought to mull over.
Please do.
For centuries, human beings have looked up at the night sky, seen the glowing stars in the dark, seemingly empty voids between them, and confidently assumed that what our human eyes could perceive was the totality of reality.
It's human arrogance, really.
It is. We literally built our philosophical and scientific understanding of the universe around our own biological limitations. But a machine like AtLAST reminds us that the universe does not cater to human eyes, and it does not operate on our visual spectrum.
Right.
The most important world-building events in the cosmos happen in the dark, shielded by veils of soot, radiating in frequencies we cannot physically feel or see. So, as humanity prepares to open this new 50-meter window onto the cosmos in the coming decades, ask yourself, how many of our most stubborn, fundamental beliefs about the universe, or perhaps even about our own place within it, are simply the result of looking through the wrong kind of light?
That is a deeply unsettling yet incredibly exciting thought to leave on. It forces a complete perspective shift. Keep questioning the dark spaces and remember that just because you can't see it doesn't mean it's not the very thing shaping everything around you. Keep looking up and keep questioning what you can't see. Thank you for joining us on this exploration.